All right. So, in order for you to make the light bulb light up, you needed a wire to connect the two. Okay, I only gave you one wire, but you get the idea. Complete circuit. So loop, electricity has to come back, like start and come back home. So how does electricity in circuits compare to electricity that we just studied with static electricity? So static electricity, static means stationary. Like that's the meaning of the word static. Like a statue is static. It doesn't move. So when you have charge that doesn't move, that's static electricity. Some, like we talked about, when it does move, it transfers in spurts and bolts and sparks, like just momentary, instantaneous. Versus the electricity you find in circuits is a steady flow. Okay, so that's really the biggest difference between the two. Good with that? Okay, it's just kind of like you turning on a water fountain and just holding the button. It's a steady flow of water, steady flow of circuits. So a popular analogy for circuits looking at electricity is comparing that to water in a pipe, like water flowing through a pipe. So our first measurement is, as promised, electric potential difference, or voltage. So it's the comparison of electric potential from one spot to the next, how crowded the electrons are from one spot to the next, how much energy the electrons have from one spot to the next. It's a comparison. A lot of times you'll use the word across. So the role that voltage plays is it motivates the electrons to flow. How motivated electrons are to flow. In the water analogy, voltage is compared to pressure. Specifically the difference in pressure. So if you had a pipe of water and you had 100 psi over here, pounds per square inch, and you had 100 psi over here, which way would the water flow? Hundred over here, 100 over here. Which way would the water flow? It wouldn't. It'd be pressurized, but there would be no flow because there's no difference in pressure. But if there was 100 over here and 70 over here, which way would the water flow? Because there's a pressure difference of 30 from this point across to this point. Now, if I made it 100 psi and 50 psi, which way would the water flow? 150. Still this way, but it'd be more motivated, there'd be more water flowing because the pressure difference is greater. You okay with that? Okay. So that is voltage. So in chemistry, do you remember how they introduced an electron orbiting the nucleus of an atom, kind of like the moon orbits the Earth? But then later on, they're like, just kidding. It's not like that. It's like an electron cloud, and it's just all over the place, but it's in that general vicinity. Remember that? Okay. Sorry to bust some bubbles, but that's how it actually works. I'm going to tell you the simple model of a battery. It's not how it actually works, but it's a workable model. Okay. So in a battery, you have this impenetrable wall, separates the positive and negative side. It's a quick little thing. The positive side, that always has the bump. Okay, just battery etiquette. I don't know what you call that. Like, that's just how batteries are designed. Okay, dots are electrons. If you're an electron, where would you rather be? Positive side or negative side? Positive side. Do you see how there's an electric potential difference from here to here? Okay. So, but they're not able to do this because this is impenetrable. But if you're able to connect the two, would they take it? Yep. Ping. Get with that. Okay. Now, to make a connection with life, what is the voltage, the electric potential difference across the positive and negative terminal of a AAA battery? Anybody know that? 1.5 volts. Okay. How about a double A? 1.5 volts. Isn't that for a triple? Yep. Same as a double A. What about voltage of a C battery? 1.5 volts. How about a D? 1.5 volts. How about a 9 volt? 9 volts. Okay. Get to that. A cell phone battery is around 4 volts. A laptop battery is around 15 volts. A car battery, 12 volts. The outlet, 120 volts. Just to give you an idea how everything in your life compares, like with the voltage, how motivated the electrons are to flow. Good with that? Give that one a shot. Correct answer is? Correct answer is C. There is no electric potential difference. There's no difference in electric potential. Yeah, but these batteries, the circuits don't eat the electrons. They're still there. Do what?
So when they die, when they get
Okay. So here is, so that's the simple model. In reality, here's what causes the battery to do what it does. If you were in honors chemistry, you studied electrochemistry. You remember salt bridge? Okay, that was how batteries work. There's a chemical reaction. Sorry, there's a momentarily silence there. The correct answer is C. Electric potential difference is 0 there, and they're equally crowded. So how a real battery works is a chemical reaction that during the chemical reaction, there's part of it that likes electrons, and the chemical reaction produces those electrons, and that's what motivates the flow. So inside a battery, there's chemicals, okay, and when it runs out, it's like you have that limiting reagents type thing. You kind of run out of the chemical reaction. Okay. So this always causes people to ask, well, what about a rechargeable battery? Correct answer is B. Beautiful babies. Okay. There's such things as a chemical reaction that is reversible under certain conditions. So rechargeable batteries are special. They're designed to have there's a reversible chemical reaction that takes place when you plug it in. Okay. So the next type of measurement is current. Current, the variable for current is a capital I. Good. The equation for current is delta Q over delta T. And this is the amount charge going past a point each second. The amount of charge going by a certain point every second. Amount of charge going past a point each second. The unit of current. What's the unit for Coulomb? And what's the unit for time? So coulombs per second gives you an ampere. Ampere. Sometimes shortened as amp. This is different than the amp that you plug your electric guitar into. Okay, that's short for amplifier. This is short for amp. And the symbol for amp is a capital A. Good with that? Good. Correct answer is B, bountiful buffaloes. Okay, so current does not measure how fast the electrons are going, but simply how many. So let's say this is a wire. Here's a cross-sectional area of that wire. What current measures is how many electrons go by that point every second. So an analogy would be, let's say that you were hired by the Department of Transportation to measure the current on I-65. One way to do that would be to stand on an overpass and count how many cars go underneath your bridge every second. 1, 2, 3, 1, 1, 2, 3, 4, 1, 1, 2, 1, 1, 1, 2. Does that make sense? You're not standing up there with a radar gun. You don't care how fast they're going. You care about how many. Okay. Is it possible for fast-moving cars to have the same current as slow-moving cars? Tell your neighbor how.
How many per second? Yeah, how many per second? So if it's not they're slow and they all go by the same time, like they go, 5 cars go by, right? So that's something
Correct answer is yes. It is possible fast and slow moving cars can have potentially the same current. So you can be like 1, 2, 3 fast moving cars versus 1, 2, 3 slow moving cars. If fast moving cars are spread apart versus slow moving cars are closer together, you can have the same current. Okay. So did you know that current in a river is measured the same way? It's not how fast the water is moving. They measure current in units like cubic feet per second or gallons per second, some kind of volume, CFS, cubic feet per second. It's not how fast the water is moving, but it's about how much is moving, the amount of water moving by a certain point every second. Good with that? Okay, so how fast, Mega? That was a good question. I think what they do, they'll measure it based on the height. Like they'll know if the water is at a certain height at a certain point, they'll know how much volume goes by that every second. Like once they've figured it out, they'll just go by height, I think. But to get the baseline, they probably measure the speed of it. And the cross-sectional place of that river and calculate it from that. So how fast do electrons go in a circuit? So when you flip your light switch on, how long does it take the light to turn on? Right? It's not, you turn on, it's like, hey, wait for it, wait for it. There it is. Okay. It's kind of a misleading example. Correct answer is really slow. Okay. So in the springtime, let's say you want to hook up your garden hose. So you hook it up to the spigot, turn on the spigot. Do you get water coming out instantaneously? No. You got to wait there a while. It's like, come on. And then all of a sudden it's like, like, all right. Then, let's say you turn off the water. Put your thumb over the end. And then you turn the water back on, take your thumb off. How quickly does the water come? It's like the water's moving the speed of light. It's like, whoa! Like, no, that's dumb. It just got bumped out. The next guy just bumped him out. Does that make sense? So get this. A wire is already pre-filled with electrons. Okay. So they should like advertise that at like Lowe's or Menards, like on the packaging for wire, like electrons included. Like, no way, that's so good. I don't even know where I'd get electrons and be like that. Whew. Okay. It'd be like buying a hose pre-filled with water. So you turn on the light switch, just bumps the next guy out. Good with that? Okay. So how fast do electrons actually travel? So the life of an electron in a wire is pretty rough. So in the wire, you've got this crystal lattice of the wire with the metal. It's a bunch of protons. The electrons have to navigate their way through this thing. And it's a violent life. It's like they hit things, a bunch of things. Okay, they ended up drifting this way, and between collisions they're going really fast, but this is known as electron drift, and this is approximately 3 millimeters per second, or like 1/8 of an inch per second. Pretty slow. Good with that? All right. So if we were to hook this circuit up, which way are electrons going? They're going out of negative, right, through the light bulb and into positive. However, if you were to talk to any electrician, you ask them, hey, which way does current flow? All of them will tell you out of positive and into negative. In the opposite way, the electrons are flowing. And then you ask, but why? What's flowing out of positive into negative? And I would say nothing is going in that direction. And then you say, well, why do we do that? And I tell you, it's not a good reason, but here's the reason. If there's one thing in physics I could change, it would be this discrepancy. Okay. Here's why this came to be. Ben Franklin, back in the day, was one of the pioneers of electricity. He had this theory, this hypothesis, that charged particles, or there's charged particles, positive and negative. You can't see them; they're so small. Though. And he's like 50-50 shot. He guessed the positives moved, and they came up with a bunch of theories. They tested them. All his tests held like they were good. It's like it could explain a lot of things. And so the science was being developed around this idea that you have charged particles that are microscopic. Later on, we actually verified, yep, they're charged particles. But the things moving are electrons, which happen to be negatively charged. And then we're like, oh, well, shoot. You know, it's worked for decades. Like, why fix it? Like, it's good. Like, think of all the textbooks we'd have to change. I mean, it's just a subtle detail. Like, it's fine. Like, and so we went with it. Like, that's the reason. Is like, people are like, well, it works. You just don't fix it if it ain't broke. I'm like, it's broke. So, here we are. I'm the bearer of bad news. You just gonna have to deal with it. So there's one year I was like, I'm gonna change physics. Like we're gonna start with this generation, and we're gonna like overthrow this stupidity. And I taught them the right way. They come back to me next year like, Mr. Smiley, why did you teach us that way? Our physics professors like ridicule us, like tell us we're idiots. I'm like, so I'm teaching you both ways. If I ask you, what is the direction of current? You will tell me out of positive into negative. If I ask you, what is the direction of electron flow? You will tell me out of negative into positive. But is there anything flowing in the direction of current? No. Just get over it. Like, I don't know what else to tell you. Like, it's just the way that we decided to describe this. Even though there's nothing moving in that direction, the opposite direction of electron flow. Yep, current goes out of positive into negative. An electron flow goes out of negative into positive. Okay? Good at that. All right. In case you forgot which way is counterclockwise and clockwise, there's a clock right there. Tell your neighbor. Correct answer is B, clockwise, out of positive into negative. Okay. So the third measurement is known as resistance. The variable for resistance is capital R. Finally, a variable that makes sense. The unit for resistance is ohm. The symbol, abbreviation for ohm, that's the fun one, capital Omega. You're going to have to, that takes a little bit of practice to make. Okay. So resistance has to do with the material is flowing through. It's the whole like conductor versus insulator. Things that have a high resistance are insulators. Those that have a low resistance are conductors. But the reality is it's not a binary thing. It's not like a black and white. Oh, that's a conductor. That's an insulator. It's actually a spectrum. So like gold is a better conductor than copper. Copper is a better conductor than steel. Steel is a better conductor than water. Water is a better conductor than wood. Wood is a better conductor than plastic. You can flip that on its head and say plastic's a better insulator than wood. Wood's a better insulator than water. Water's a better insulator than steel. Steel's a better insulator than copper. Copper's a better insulator than gold. It's a spectrum. Okay? All I want you to know from that is it's not just a black or white thing. Shades of gray. Okay? All right. So we like to draw symbols for things. If you ever seen an electric diagram, it's known as schematic diagram. They come up with symbols. So that's the symbol for a battery. Long stick and a short stick. The short, here's how I remember it. The short stick's negative. It's only one stick to make a negative sign. It takes two sticks to make a positive sign. Good with that? A resistor is like kinks in a hose. So to draw this circuit in schematic diagram wise, here's your battery. Wires. The light bulb's a resistor. It's the resistance. That's that circuit. Usually you draw wires like at right angles. Makes a complete circuit. Complete loop. Good with that? And lastly, Ohm's law. Super important equation in circuits. Voltage is equal to current times resistance. A way to describe this conceptually is rearrange it like this. Voltage over resistance is equal to current. So voltage motivates electrons flow. It's the push, it's the pressure. It's like, come on, let's go. Resistance, resist electron flow. Like, come on, whoa, whoa, whoa. Do you see the conflict of interest here? The battle that goes on. It's like, come on, like, whoa. The result of that battle is current. So is the flow of electrons. Okay, the result of that battle. So what two ways could you make current increase? Increase voltage or decrease resistance. Got a worksheet due tomorrow.